Now that man has learned to package and control a vastly greater force than chemical explosives, his thinking has turned to methods which will make possible the effective use of this new power within industry. The potential applications? Consider just one: the development of a harbor in the hard rock of a remote coastal area. Assume a channel approximately 400 meters wide, 1,500 meters long, and at least 20 meters deep, with a turning basin of 1,000 meters diameter, having a depth of at least 20 meters at its shallowest point. The procedure? Bury an inline series of 4 equally spaced 100 kiloton shots at a depth of 30 meters, and a terminal shot of 1 megaton 50 meters deep, all shots of minimal fission yield. Dependent on the nature of the surrounding medium, surround the devices with sufficient borated compounds to reduce neutron activation by several orders of magnitude. Detonate. What is the effect upon radiological safety in the area? Using energy releases of the order of a megaton, buried at a depth of 50 meters, with the fireball contained, there would be minimal thermal effects above ground, and burial of the energy source would confine the radioactivity to a smaller area than a surface burst. Overpressures and seismic effects would be acceptably small beyond a radius of 30 kilometers. Activity in the region of the crater would be washed out into the ocean rapidly and essentially removed from the biosphere. The activity on land near the crater would rapidly decay. And in the matter of economics, the volume excavated would be about 100 million cubic meters. The estimated cost of excavation with nuclear energy releases would be significantly less than the estimated $60 million that it would cost for excavation and removal by conventional means. It is interesting to note that the cost of the explosives in the nuclear energy release would be but a small fraction of the total expenditure. In remote regions where large yields can be safely used, and where economic factors are favorable, such explosions are demonstrably feasible. With more experience and the extension of low-cost reduced fission design to smaller energy releases, the method may one day be applied in more highly populated areas. In the state of Nevada, one of the table-like mountains was the locale of the first completely contained underground nuclear explosion. The 1,700-ton shot was fired on September 19, 1957. Watch for the shock waves above the arrows. Rocks dislodged from the mesa's rim left dust trails that formed into a cloud above it. The ground shock was so slight as to be almost imperceptible to observers 4 kilometers away. The peak acceleration at this point amounted to 0.02 Gs. Actually, only 0.5% of total energy released was found to be in the seismic signal, and no significant overpressures existed. Subsequent construction of an exploration tunnel to zero point permitted close study of the explosion's effects and provided data on the problems of mining in comparable regions. A graphic illustration of the site, with a section removed, permits visualization of the physical setup at zero point. The tunnel, greatly enlarged for the purpose of illustration, was designed to be self-sealing to prevent the ejection of radioactive material. The initial rectangular room which housed the nuclear device was approximately 2 meters on a side. The shock from the explosion in the room collapsed the tunnel a distance of 61 meters from the point of detonation before the shock could progress down the tunnel itself. A profile view of the site, a formation of porous silicate rock known as Oak Springs Tuff, which overlays a dense crystalline limestone, permits relation of the location of 0 point. 610 meters from the tunnel entrance, 244 meters from the nearest point on the slope of the mesa, and 274 meters from the mesa's top. When the shot was fired, the walls of the initial rectangular room were expanded by a pressure of about 6 megabars to a sphere with a 17-meter radius. The sphere was lined by about 10 centimeters of melted rock weighing 700 tons, which reached a temperature between 1200 and 1500 degrees centigrade. The shock, continuing outward, crushed the rock to sand for an additional 20 meters. Because the formation contained about 15% water, the melted rock cooled rapidly to form glass, which contained the radioactivity. When the roof of the glass sphere gave way, a collapse proceeded progressively upward and stopped only after rising about 120 meters above 0 point. In the matter of mining in comparable regions, it is noted that the shot produced about 400,000 tons of sand. The collapse of the initial cavity resulted in more than 200,000 tons of permeable rock, and that of all this material, only 700 tons contained practically all the radioactivity, and this in a well-defined, localized zone. These facts immediately suggest a whole series of possible applications in diverse areas. For example, firing in a dry medium could result in a high-temperature region that would persist for an extended period. And the controlled introduction of water would produce steam for use in generating power or for other industrial purposes. The use of explosions deep underground beneath large low-grade ore bodies such as copper immediately suggests more economic recovery, as the explosions would break and loosen large volumes of the ore to permit leaching of the mineral. The possibility of releasing petroleum from oil shale by detonating a device beneath the shale layer is suggested by the fact that in the shot at the Nevada mountain, most of the energy was released as heat within a radius of about 30 meters of the center of detonation, and the volume of broken rock was considerable. The crushing and heating would distill petroleum through pipes to the surface. In the area of public service, it is suggested that explosions in dry river valleys, in desert areas, would provide large underground reservoirs, which would serve for flood control and for recharging underground water supply systems. Of course, there are problems to be solved, and experiments are underway to solve them. In sum, nuclear explosives will be used within industry for the good of man exactly as chemical explosives are used. But in addition, they will be used with an enormously greater effect at a substantially lesser cost. And for many industrial applications which require amounts of packaged energy heretofore unavailable.